Okay, gonna be doing a couple questions today, right now, anyway. So these are the first two. The first one we're gonna do is the chapter 11, number 2, which I highlighted. So we're gonna figure out how much energy does it take to convert 89 grams of mercury to chloride to vapor at its boiling point of 302 degrees Celsius if the heat of vaporization is 57.82 kilojoules per mole. Okay, first thing to take notice of is that this number is not really important to us right now, because all it's saying is that this liquid mercury 2 chloride, it's already at this temperature and it's just going through boiling, essentially, just going to be vaporized. So this number isn't that important. You'll see that over here because I didn't write it down. Okay, go back and remember that Q, which is what we're looking for, right, is heat. Q for phase change is N times delta H, well, Q vape specifically, is N times delta H of vaporization, right? And this N is the number of moles. Okay. So we have this, we just got to figure out what our N is. Okay. Well, to do that, we better figure out what the chemical formula for this is, because we need molar mass. Okay. So go back in your memory logs and nomenclature. Remember that mercury 2 means, okay, at mercury, and then this 2 tells me it's 2 plus. The charge on this mercury is 2 plus. And then chloride or chlorine is Cl minus, right? Because it's in the 7th column and just wants one more electron. So that means that the chemical equation, right, is I do my cross thing. So HgCl2. That's what I get in total. Okay, so we need the molar mass of this guy. Molar mass is 271.49 grams per mole. Okay. Right, so now it's easy to find the moles. So 89, so I have 89 grams HgCl2 for every 271.49 grams of HgCl2. Get 1 mole HgCl2. So that means I have what? 0.328 moles. Okay. So we got our N, have our H, so now we can get Q. Just plug and chug. Okay. So I take 0.32 grams, 328 moles times my 57.82 kilojoules per mole. So Q vape is going to be I guess I should be politically correct. Let's do 33 right there. 33 because I went 2 sig figs. Well, there I wanted 2, so here I also want 2. 19 kilojoules, and that is our answer. Okay, next question. Chapter 13, number 2. So we're going to figure out what is the vapor pressure of solution containing 407 grams of glucose and 821 grams of water. Okay, at 32 degrees Celsius. All right. Okay, so I wrote those down over here. All right. Some kind of things he'll probably either tell you, he'll most likely tell you. So glucose is C6H12O6. Okay, so he'll either give you that on the test, or he'll give you that on the test. Okay. So if we go back and think about our colligative properties, you'll see that the vapor pressure of your solution is equal to the mole fraction of your solvent times the pure vapor pressure. So this is the vapor pressure of the pure solvent, right? Okay, it wasn't given to us in the question, but he'll give it to you if you need it. Probably just forgot about it, but I'll go show you where I got it from, so you know I'm not just making it up. Right here's a nice little vapor pressure chart in torr. So we go down to 32 degrees right here, and we see it's 35.7 torr. Okay, so now we have that. So now we are ready to roll. Okay, first things first. Okay, mole fraction. So for my mole fraction of solvent, so in our case it's H2O. I'll put that instead of solvent. For us is H2O, right? That's the one that's the majority of the solution. So our mole fraction H2O is going to equal the moles of H2O plus the moles of glucose over the moles of H2O. Okay. All right. Okay. So let's figure that out. So let me get the molar mass. We know the molar mass of water, or you could calculate it. It's 18.02 grams per mole. Molar mass that guy. Let's see. It's 180.156 grams per mole. So, okay, let's see. So we have 407 grams of C6H12O6 for every 180. Give myself more space. So we have 407 grams of C6H12O6 for every 180.156 grams, you get 1 mole. So that's going to give us keep 3, so 2.26 moles. And then for water, we have 821 grams of H2O. And then for every 18.02 grams, I get 1 mole. So I get 45.6 moles. All right, now we have those two numbers, so we can go back up here. Say, okay, so that's going to be 45.6 plus 12.2 times 6, and over 45.6. So I get my mole fraction of H2O is what? Let's see. That divided by, oh, let me do this plus this, and then this divided by that. So I got 0.953. Okay. All right, now we're final stretch. So now I go over here. So I say, okay, so that's equal to 0.953 times my 35.7 torr. So I get P vape equals 34.0 torr. think in this thing he gets on the sheet it's 34.1, but this is, he probably just uses a different, either he uses a different solvent pressure, vapor pressure, or maybe his molar masses are slightly off from mine, but that's close enough for a hand grenade. Okay, last question. Okay, right here, we're going to determine the solubility of calcium fluoride when we add 0.1 molar sodium fluoride to it, and we're assuming no volume change, so don't have to worry about diluting this concentration right there. Okay, so go look up here at the equation above to get the Ksp, right? It's right there. So we got it. Okay, so we go over here, have my Ksp, and I told myself what we're doing. All right, so write the formula that's going to happen. So it's our normal Ksp equation where we have CaF2 solid goes to Ca2 plus 2F minus. These are aqueous. You know they are. Okay. Then we do our ice table, right? Ice table. Ce. Don't care about that because it's a solid again. Okay. Here, 0. No calcium's floating around in there. Here, though, I have this floating around. It's going to completely dissociate into F minus and the sodium. But here we have F minus, so I need to put 0.100 molar. Okay. All right. Then, okay, I have a 0 right there, so I have to add S to this side. Plus S plus S. Okay. So I get S 0. Ooh, almost made a mistake right here. You guys aren't here to tell me. So 2S right there, right? Okay. Plus 2S because of that coefficient. 0.100 plus 2S. Okay. And then we would normally proceed by solving for our Ksp. We set things equal, right? So I have that the Ksp is 3.9 times 10 to the negative 11 equals this one, S times 0.100 plus 2S squared. Okay. All right, look at this. S right there. Right, only S. So here I have 10 to the negative 11, 10 to the negative 1. So I'm going to assume S is small here. Make this a whole lot easier on myself. So I don't have to solve a cubic, essentially. This will turn into a cubic. Get rid of that. I'm assuming S is small. Okay. All right, so this equation turns into 3. Don't get rid of that one because it's not being added to anything. This one is just being multiplied, so I keep it. So 9 times 10 to the negative 11 equals S times whatever 0.1 squared is. Let's see. It's 0.0100. I'll keep the 3 sig figs. Okay, so that gives me S equals let's see, 3, 6, so 4.0 times 10 to the negative 9. But again, we have to check it first. We have to make sure that's valid, right? So I take my, ooh, excuse me. Okay, so here it's a little wonky. No, it's not. I take that. I take S. So I take my 4.0 times 10 to the negative 9 divided by by 0.100, right? We take the change divided by that and make sure it's less than 5% times 100. Okay, and that's most definitely less than 5%. Okay. All right, so that means this guy's good. So here's our answer.